Hello, everybody. Welcome to today's current seminar. Today we have one speaker, one talk. Our speaker today is Xin-Yang Liu. He will be giving a talk on integrating PDE operators into neural network architecture in a multi-resolution manner for spatiotemporal prediction. Xin-Yang Liu is a PhD candidate in the Department of Aerospace and Mechanical Engineering at the University of Notre Dame, supervised by Professor Jiancheng Wang. He earned his bachelor's degree from Xi'an Jiaotong University, China in 2019. Xin-Yang's research adeptly combines advanced deep learning methodologies with computational mechanics. His focus is on modeling and controlling complex spatiotemporal dynamics, including turbulence and fluid structure interactions. With that introduction, the floor is yours and you can start your presentation.
Yeah, thank you. Thank you for the nice introduction. And today I'm gonna talking about integrating PDE operators into neural network architecture design. So today's talk will mainly talk about two works. One is PDE preserved neural network, or PDE in short. Another is the ongoing research project called the multi-resolution finite warming inspired neural network, or MurphNet in short. Okay, so I would like to thank my collaborators. You see here. Okay, so first, some background. Spatial temporal dynamics are very common in multiple physical processes, such as heat flow coupling or turbulence or fluid structure interactions. And traditionally, we will use numerical methods to solve those physical processes. But traditional methods or numerical methods can be very challenging in some circumstances because sometimes it can be very computationally expensive, especially if we want to resolve those spatial temporal dynamics in a very high resolution. And which those high computational costs makes it infeasible for tasks which requires multiple repeated model parts, such as uncertainty quantification, optimization, or design or inverse problems. Fortunately, with the rapid development of data-driven models and all those GPU computing and the deep learning algorithms, we have new approaches to tackle this spatial temporal dynamics modeling, which is a pure data-driven deep learning methods. However, although they are powerful, there are some issues if we apply those pure data-driven methods to predict those spatial temporal dynamics. Say, for example, here I show a comparison between our pure data-driven model, which is convolutionally based next step predictor, compared with its CFD or training label data. So as you can see here, as the first few steps, the pure data-driven can give a relatively good predictions. However, as the model rolls out, the error accumulated and soon is dominated by some artificial noise. So except for this error accumulation issue, those pure data-driven methods also suffers from poor generalizability in out-of-sample regimes, the unseen parameters, the unseen initial condition, boundary condition, all those stuff. And also the training cost is really high because we are only depending on the data and we are kind of training from scratch every time. But luckily, we are working in a scientific machine learning community, which means data is not the only information that we can leverage to train our deep neural networks. Say, for example, in the fluid problems, we know that the system is actually governed by the Navier-Stokes equation. And for some even more complex systems, even the governing equation is not fully understood. We still have those basic physical laws such as mass or energy conservation. So those are the valuable and high quality physics priors that we can leverage in the deep learning, but how to leverage them? So that leads to a very famous work called the physics-informed neural network PDE. So I believe everyone here has more expertise in the ping, so I will just give the details of the physics-informed neural network. And I just describe the ping in one word. I would say ping leverage the physics prior by regularizing the training using those physics or Garmin equations. In other words, it's trying to minimizing the PDE residuals during training. So yeah, ping has been demonstrated to be a very successful method. But here I want to maybe introduce another alternative direction of leveraging those physics priors, which with embedding the physics into the neural network structure. So before I introduce the entire structure of how to embed in the physics, I want to first review the relationships between those numerical operators and neural networks. Say, for example, here we use a very basic component of modern deep learning, the residual connection. So this schematic shows the residual connection, while the FN just is a general representation of different deep learning neural networks such as MLP or CN or transformer. Okay, if we write out the mathematical equation of this schematic, it can be expressed in this way. So if we have like infinite small delta t here, then it can be actually represented by this ODE. So in other words, if we have like infinitely deep residual networks, it can actually represent an ODE. And on the other way, an ODE, if discretized using finite steps, then it can be represented by a residual network. Okay, so this is about the temporal operators. Now, how about those spatial operators? In PDE, we also have to deal with those spatial differentiations. Then say, for example, I want to calculate this derivative. Then if I discretize it using finite difference and write it as kernel form, then this differentiation can be represented by this 3x3 kernel. If we apply this kernel to a computational domain, then we find that it actually shares the exact same behavior as a convolution neural network. Okay, so by now we have showed the representation of those differentiation operators presented in a partial differential equation, PDE, and how can we use neural network structures to represent them. So those findings are like proposed by like previous works like NeuroODE or universal differential equations. But those papers are majorly talking about general computer science tasks. The underlying system they want to learn is not necessarily actually governed by those ODs or PDs. But here, we believe that if we are trying to, if we're embedding those structures into a neural network, which is targeting to learn those systems that are actually governed by this OD or PDs, we can achieve a very good performance boost. Okay, so then let me introduce our work called the multi-resolution partial differential equation preserved learning framework for spatial temporal dynamics, or we call it PDE in short. So in this work, we propose a new architecture called the PVN, which consists of two parts. One is represented by this light blue box, which is called the PD preserving part. By PD preserving, because we are using those prescribed convolutional filters to representing those spatial derivatives, and they are mathematically equivalent to those finite difference operators. And besides that, we also have a large skip connection to represent those temporal operators. Okay, so this is the PDE preserving part. And to reduce the computational overhead introduced by this PDE preserving part, those things are actually only working on a downsampled field, not on the original high resolution. Because if you don't downsample it, if you just apply the exact same operators on the original high resolution field, you are actually having a full resolution numerical solvers. So that will also like slow down your prediction. We don't want a very high computational overhead. So we decide to like only apply those operators on a low resolution field. Yeah, so that's about the PDE preserving part, and the upper part, bounded by those orange box, is our trainable part of the PBN. So this is a convolutional based neural network, and trying to like correct the errors that may introduced by this low resolution representation of the PDEs. So by adding all those things up, we can get our overall structures as the PBN, which maps from previous step result to the next step result. Okay, so we then apply our PBN to several different spatial temporal dynamics. First is 2D Burgers equation. So in this case, we parameterize both the viscosity as well as the initial condition. So the initial condition is written here, and it's a very high dimensional initial condition space. And during training, we just use like 16 different viscosity as well as the first 100 steps to train those deep learning methods. Yeah, and here I want to mention that for fair comparison, the black box method is actually sharing the exact same structure as our trainable part of the PBN. Yeah, so here the left side shows the testing result or the relative error of the baseline model, which showed represented by this orange line, compared with our PBN result. So this result is tested on training initial condition and the training viscosity. So those initial condition and the viscosity are a thing, but we also extrapolate them in time. So as you can see, even within those training stage, PBA already shows a very low error accumulation compared to the baseline method. And once it goes to the extrapolation in time, it's the advantage of PBN becomes even larger. So the shaded area here just represents the maximum and the minimum values of all those different testing cases. Here we tested on like 100 different initial condition and viscosities. And you can also see that the shading area for the PBN is very small compared to the baseline method. It's almost unobservable here. And the right side shows the testing error on unseen initial condition and unseen viscosity. So in this scenario, the PBN just have even larger advantage over the baseline method, which means our method can actually generalize very well compared to a pure data-driven method. Okay, so here I just show more contour comparison. I randomly picked 4 different unseen initial condition and unseen viscosity. So the capital T here means training length, which equivalent to 100 steps. So yeah, as you can see, even within those training range, the black box method already like diverged from those ground truth reference, while our PBN have a very good predictions. Even the model is shown out for like over 2 times longer than the training set. And it's the same case for all those different initial conditions, different viscosities. Okay. And also, we made a comparison between the PBN and other famous neural operators or those other deep learning methods. So this first top figure shows testing errors. Yeah, we still test on the same case, the 2D Burgers equation. And those dashed line shows the testing results on unseen initial condition and unseen viscosities, while the solid line shows the results on seen training initial condition and viscosities. So as you can see here, our PPN, for our PPN, the dashed line and those solid lines are almost the same, just a very negligible difference. Well, for all the other cases, the solid line has significantly higher relative error than the dashed lines, which means that those models cannot perform very well on those unseen initial condition or unseen viscosities. And also in time, the error accumulation rate of our PDN is very steady and robust among all those different time steps, even it's like not within the trending range. Yeah, and also the computational cost is not high by adding those PDE preserving parts. As you can see here, the memory efficient, it's actually efficient in both memory cost and the inference time cost. So PBN is among the top performer here. So yeah, this is about.
Xin-Yang, I have a question.
Yeah.
So you tie, this is very good. You tie it to a certain stencil, a certain grid. So clearly, if you change the grid, you will change find different results. You have to change the grid, otherwise you don't preserve that even approximately the structure of the Laplacian unless you have the 5-point stencil.
Mm-hmm.
So if I go in and do a test with my own grid, a structure grid, let's say, how do I use the method?
You mean changing the grid size?
Not just the size, the structure.
Maybe unstructured mesh. Yes,
yeah.
That will be a limitation of our work. We have to admit that, yes, the ping or those numerical neural operators, we generally consider they are more like a mesh irrelevant thing. But here, yeah, this method as a current format list, it still requires a structured mesh.
Yeah, so because you actually, it's kind of, it's called numerically informed. The correct characterization, numerically informed, not structure, because you don't actually preserve the structure.
Yeah. If you, it's more appropriate to say numerically preserved, not physics preserved. Yeah, we only preserve the discretized form of those Garmin equations, right?
But you depend so strongly on that's what I'm saying. If you do a structure grid on the same random points, you will get totally different results.
Because
the structure is not preserved. There's no way you can have the structure, a discrete, coarse discrete Laplacian. It will not be preserved in a unstructured, fine grid.
Well, yes. It's also a limitation of the finite difference method. Yes, finite difference method. Yeah, it's just struggle to handle those unstructured mesh. Yes, but here this paper is just our first attempt in this direction. So there's some limitation. Yes. But also for those method, for those unstructured mesh, one alternative way maybe to just remesh it, just projecting to a regular mesh, then we do the prediction, then we definitely will sacrifice some accuracy. But yeah, still we have some alternatives. But yeah, we have to admit there's also some limitation, right?
Also for the inverse problems, if you're trying to discover like a gray box models where you're trying to discover part of the operator, you don't know what the operator is. So you cannot. Let's say you're solving an inverse problem, right? The inverse diffusion, and you're trying to find the diffusion operator, the Laplacian operator. You know what structure to impose because you don't know that it's Laplacian.
Right. So you mean if the Garmin equation is not known or not fully understand, then we cannot. Yes, right. So this method is just more about constructing a surrogate model. So that means we already knows the equation, at least partially knows the equation. But our flexibility here is we are not fully rely on the embedded structure. So if if you can see here, yeah, this one. We not only have the preserving part, we also have this trainable part, which means if you have some like operators that is not preserved in this preserving part, we can still like using this trainable part to compensate for those missing operators. So
Right.
I will have a brief introduction of the cases, but I will show it later. So
okay, thank you.
Yeah, thank you. Okay. So where am I? Here, yeah, right. So yeah, let's move to the next case. Yeah, it's next case we tested on a 2D jet flow, which is governed by the Navier stocks. So in this case, we parameterize both the Reynolds number, or I would say the viscosity, as well as the jet position. So the jet position will be fixed during the simulation, but we parameterize its positions, and the direction of the jet flow will be changed, will be following a sinusoidal curve during the simulation. So here, just to first show a video of our model rollout. So first line is the CFD reference, and second line is our PPN results. Yeah, I will also want to mention that this two jet position and Reynolds number actually unseen from the training set. And yeah, as you can see, those black box methods, the error just accumulated very quickly, and it's just diverged from the ground truth at the later time steps, while our PPN gives a very consistent predictions among all those steps. And this model has been rolled out for like almost 3 times longer than the training set. So the performance is very impressive considering the time length I extrapolated. Okay, so here I shows the relative error of our PVN method and baseline method. Here we just use the first 75 steps as the training, as a training set, and we only train like for 6 different Reynolds numbers and 8 different jet positions. Yeah, as time before, the black box one suffers a lot from the error accumulation issues, even before the time extrapolation range. While our PPN remains a very constant error rate, even it's drawn for like 3 times longer than the training set. Okay.
Excuse me. Hi, I have a question. This is Panastinis from Pacific Northwest National Lab.
Oh,
so do you enforce the physics during inference or only during training?
It's like I would say like our structure, if you say this, it's we use the same structure. We use the same structure both during the training and the inference. Okay, this is our entire structure. Yeah.
Okay, so during the inference, you do enforce the light blue box there, right?
Right. So you can see, yeah, we are mapping from this side to this.
A related question then is, how is this different from just using a finite difference scheme?
Yeah.
All I'm saying is, what does the light blue box give you in addition to a finite difference scheme?
Sorry, I didn't fully understand.
The light blue box uses, I see there the divergence, the Laplacian, etc. Right? So if you know the PDE, you can use the light blue box to estimate through different stencils the different differential operators, right?
Right.
And then you make a prediction, which you do some upsampling, and then you feed into this summation that you have there, right? So, so the only difference is that this light blue box operates at a coarser level instead of the original resolution.
Right.
So why, I mean, I'm trying to understand where is actual, what do the neural networks give you in addition to a finite difference scheme?
So I assume you are talking about if I just using the finite difference from the original resolution.
Yes. So what extra do you get here?
Yeah, the extra here is the speed up. That's the most important thing. So I didn't have the result here in the slides, but if you can check our paper, we showed that compared to the numerical method, we can speed up for over 100 steps, 100 times, sorry. Yeah, and I know lots of deep learning methods can achieve even higher speed up ratios, but the issue for them is that even though the speed up ratio is high, but the prediction is not accurate.
Right.
Yeah.
But the speed up here in your case does not come from the top box, which has the convolutional neural networks. It comes from the fact that you are using the finite difference scheme on a coarser mesh.
Right. That's a very good question. But actually, what I omit here is the time step we are doing is actually way larger than the numerical time steps. Because if it's a pure numerical step, numerical solver, then we not only need to consider the dynamics itself, but we also need to consider the numerical stability issues. And most of the time, the delta t is not bounded by the dynamic itself, but by the numerical stability. Yes. So by doing this, we can roll out our model at a very large delta t. So yeah, our model can. That's another reason why our model is faster.
Okay, so you do use a coarser mesh for the light blue box, right? Then you upsample it. And then from the convolutional ResNet block, what do you get from that? Do you get some kind of prediction too, that then you sum everything together?
Pano, he gets a prediction. Yeah, that's why he compares against that upper block in his plots. He shows the upper block result. But the question is, what happens if you just use the coarse? Right.
I mean,
what is the error there?
I'm just trying to understand where is the coordination of the two parts. What does each part give you?
Manos, this idea is very similar to what Ziping Mao showed once, which was how a coarse-grained depot net can assist PIN. So when PIN does very little work and it does a good job. Remember that?
I don't remember that, but okay.
So you pre-train a depot net and for all these conditions, and then at a very coarse level, and then you use pins, but it turns out synergistically like this, exactly like this. And then it turns out that pins can do very hard, can extrapolate, can do lots of things that wouldn't do otherwise. But I would like to see as a reference, in addition to, if you go to your comparisons, Xin-Yang.
Yeah. This one, right? Oh.
Yeah, any of your comparisons where you have, here you have the black box. You say the black box. If you can go previously, just the previous one.
This one, right?
No, the one that has the visualization of the jet.
Visually, the control.
This one here. So the last one is that's the black box. That's the top block in your architecture, right? But it would be nice to also see the finite difference
scheme alone. You're right. What the finite difference scheme alone does. Yes.
Yes. So I have that in my paper.
Because there appears to be some collaboration between them that somehow gives you a better result, but I want to understand how much each one contributes, you see.
That's right.
Yes, that's a very good question. We actually discussed this in the paper. So
just to clarify, I like the results, okay? I'm not asking, I'm asking in a good way.
Here he has it. Yeah, I can see that. Yeah, okay, good. Yes. So there is a synergy. There is a synergistic effect, Panos. Yeah.
Okay. And because you have the finite difference scheme during training, somehow the neural network during training learns somehow to work along with the finite difference scheme, right?
And
that extrapolates when you use it for inference too.
Mm-hmm.
Okay.
Yes.
All right.
Yeah.
Thank you. Yeah. And sorry for the long question. Yeah.
Yeah. No problem. Yeah. I think the advantage here is, like Professor Kanadaxis said, it's kind of similar to like using the pre-trained deep neural net to assist the ping. But the advantage of this method is because we are directly embedding those original numerical operators inside, so the generalizability will be slightly better than those using a pre-trained black box method. So yeah, that will be our contributions here. So yeah, let me continue. Yeah, so I think I have finished this part. Then yeah, here comes the question that previous Professor Kanadaxis asked. So what if this equation is not fully understood? So there's some missing part. So here we test the case with the unknown magnetic field applied to this previous 2D jet flow. So this part is not embedded into our PDE preserving part. So this one is missing, or this one is completely learned by the tremble part of our PDE structure. So as you can see, still our PDE can give a good prediction, although there's some discrepancy, but still at least it's extrapolated 3 times longer than the training set and still looks physical, especially if you compare with those black box methods. Okay. Yeah, here shows the error curve here. Our PPN still remains a very low error accumulation rate along the model rollout. Yeah, then so yeah, next I just demonstrate that this PPN neural network is more like our first attempt, and it's just an idea of framework. We don't have to limit ourselves to just use those convolutional based neural networks. We can also replace it with any form of those black box method, put it into here as the trendable part, say UNet or vision transformer, those stuff. And here I just show a result of them. And in this case, to make it fair comparison, the black box baseline also becomes those the trendable part, like the UNet. Yeah, here is a typo, but this is a black box VAIT if I just compare with our PDN, and this one is using the UNet comparison. So on both cases, we also show the advantage over those pure data-driven black box method by embedding those physics operators or numerical operators into our PPN structure. Okay, so the last part, we show the generalizability of the PPN over different boundary conditions. So in this case, we parameterize the boundary condition. So this is just a simple diffusion equation, and we parameterize our boundary condition by, we have 2 types of boundary first. One is a directory, and another is Newman. And this is indicated by a C parameter here. 0 represents directory, and C equals 1 represents Newman boundary. And we also parameterize the boundary value, which is represented by the D here. Okay, so this one is a 1D case, and the horizontal direction means the spatial axis, and this vertical direction is the time. It's a model rollout time. So yeah, as you can see, the PPN can give a very consistent prediction along the model rollout, while the black box one, as you can see, maybe just here, it already got some artificial streaks there, which makes the prediction unphysical. Okay, and the error curve also reflects that. Even though this case is not that complex, but our, let's say, both models can achieve very good accuracy, but our PPN just have over 3 times more accurate than the baseline method in this boundary condition parameterization case. Okay, so yeah, this is about the PPN neural network. and if you are interested, you can read more details about those original paper. This one is our first attempt, as I said. So if you simplify the overall structure, then you can say that our numerical operators only works on a downsampled field. So by doing this, we are reducing lots of computational costs, but also we sacrifice some precision that will be embedded into our neural network. Although the transfer part of the PDE already do a very good job to like compensate or correct those quotient issues caused by those downsampling, but still have room to improve, right? So we are trying to like further push the boundary even further to improve the embedded precision of those integrated numerical operators, and meanwhile keep a negligible overhead. Okay, so to achieve this, let's look back at our computational domain. Say if I have a high resolution field like this, and we discretize into more mesh grids. Okay, so in PDE, we first do downsampling, and here, since we want to embedding more accurate physics, we do a domain decomposition instead. And by decompose the computational domain, then we can calculate the flux between each subdomain. And after we got those flux, we can then calculate the mean value, the mean changing value over each subdomain. And here just comes our the global structures of this new architecture, the MurphNet. So the global level, we have our known physics, or those numerical operators, to calculate the flux, as well as a global neural network to correct those flux, which might be, the error might be introduced by like a larger delta t, larger time steps. So we have another global neural network correct those flux. And then using those corrected flux, we have the average value over each subdomain. And since we are correcting those flux, the conservation is satisfied at least on intercell level. Okay. So, and how about those high resolution field inside each subdomain? Then we have another local neural network to like predict the local fine structures inside each subdomain. And by adding them up, then we can get the original high resolution field inside each subdomain. And if we apply those local neural networks to each of those subdomains, then we finally got the overall fine resolution predictions at the next time step. So yeah, this slide just shows the overall architecture of this so-called multi-resolution finite volume inspired neural network, or MurphNet in short. So yeah, as I described before, if we have a high resolution field, we first decompose it into several subdomains, and we use a neural network to, we first use a numerical operator to calculate the flux, and we have another neural network correct the flux. Then after the correction, we got the average value among in each subdomains. And by adding up the fine features predicted by the local neural networks, by adding them up, we can then get the fine resolution predictions as the next step. So we call this MurphNet, and we apply this to three cases. First is the Wundy-Burgers equation. So as before, we parameterize the viscosity as well as the initial condition. So yeah, compared with those black box methods, our MurphNet can achieve very low error accumulation, especially here you see, as the boundaries, those black boxes already blows up, while our MurphNet, although there's a slight discrepancy, but it's still very physical. And I have to mention that this is a result at the last step, which is 4 times longer than the training data. That's very long predictions. It's already rolled for over 2,500 steps. And also each frame is like 10,000 times larger than the numerical steps. So that it's actually very fast when you compare with numerical solver. Okay, so next, we also apply this MurphNet to a 1D QS equation. And as before, we parameterize the initial condition and oh, there's no viscosity. We just parameterize the initial condition here. Yeah, and you can see since it's a chaotic system, the error curve increased very rapidly for those black box method, while for ours, it's still like the error accumulation rate is way lower than those black box method. Okay, and next, the last case, we'll apply this to a 2D scalar Burgers equation. So in this case, we parameterize the initial condition as well as viscosity. And here, those videos shows the testing results on the unthin initial condition and unthin viscosities. And the model rollouts for 4 times longer than the training data. For this case, we only have 40 steps as the training data. And yeah, as you can see, as the last step, the MurphNet still gives a very good prediction when you compare to the label data, while the black box just gave a completely unphysical predictions, and which can be also reflected by the relative MST value as the last step. Ours only got less than 1% error, where their black box method have over 15% error. Yeah. So yeah, those are all the results I want to show here today. Yeah, so in today's talk, I just introduced 2 methods to of how to integrating those numerical operators into the neural network architecture in a multi-resolution manner, and they achieve significant better generalizability over those pure data-driven methods. I hope those 2 works can inspire future research. Yeah, thank you all.
Thank you so much for your great talk, Xin-Yang. Now we open the floor for questions. Do we have any questions for the speaker from the audience?
Can I ask another question?
Sure.
So can you explain again about the local features? How does this work? How do they know, what the correction should be? Yeah.
You mean for this MurphNet, right?
Yeah, because if you go back to the workflow that you had before, the next slide, wait, next, and the other, and one
this
more.
One?
Yeah, that one. Yes. So here you are at, let's say, time t, right? And then if you follow the lower part of this figure, then you have what you had before. You have neural networks plus known physics, right? So you get a corrected flux. But that I understand, because it's like what you were doing before, but now you do it in subdomains.
Yes,
and
and not exactly like before, because here, previously, if you remember, the trainable part, the neural network actually, it's more like this part. It's originally is already working on the original resolution, but here, this global neural network actually only works on those coarse subdomain interfaces.
Okay. Yeah. So the neural network works at the coarse.
Yes,
domain.
right.
Okay.
Just
so then you have to bring in this extra, what you have on the top, which says learned/generated local features.
Right.
So what do these take as input to output these local features? What do they need to take as input to find out what are the corrections that you have to do locally?
Yeah, this is actually not correction. This is more like super resolution, or you said fill in those fine structures.
Okay. So what does it take as input in order to be able to find this super resolution?
Oh, yeah. So just like here, I just say for one subdomain, I just taking the previous time step subdomain information, high resolution subdomain information, and gave it to the local neural network, and the local neural network just gave the fine structures within this subdomain. And then,
okay.
But those are the zero mean field.
But my concern is the following, that if you give it as an input what was the situation at the previous time step, it will provide you with some, super resolution, but it will be somehow relative to what was happening before, right? At the previous time step. It's not about the current time. I would expect that the small scale features that you have to fill in must take into account what is the current time, which is t plus delta t.
Yeah. So let's say we are predicting our velocity field at, say, t plus delta t. Then
Right.
we based on previous t data. So our assumption here is since the label data is just generated by the Boyle order scheme using CFD, then we assume that the previous step information is already enough for predicting the next step. So this is the assumption of those next step predictors. Yeah.
Okay. So somehow you don't take into account the evolution that you just computed from the bottom part of your.
That's actually in the implementation. It's not shown here. Yeah, in the implementation, we also takes the prediction as one of another input. Yeah, you are right.
Okay.
Yeah.
Okay. So you do put in the prediction.
Yeah, that's kind of like input enrichment, which is not necessary, but it will help.
I would expect that if you try to make your time step larger, you will need this enrichment. Otherwise, between the previous time step and the current time step, a lot of things may have happened at the small scale.
Right. Yeah. I agree. Yeah.
Okay.
So, because we are, the original safety solver is more considering those numerical stability issues. So the delta t is very small, and it's actually unnecessarily small when you want to just resolve those dynamics. So in this case, we actually don't lose lots of information if we just taking the previous step. But yeah, of course, if the delta t is really large, then I agree.
Yeah.
We need to take in the current step. Yeah.
Okay. Thank you.
Yeah.
So your method is similar to, in spirit, this method, to parareal method that is used by Lyon. So you basically have a global solver information that corrects these fluxes at the interfaces. I don't know if you know that method, but it's usually employed for parallel in time. It's called parareal. But I have a question on the fluxes for the Kuramoto-Zhivazinski. Did you use second order fluxes or just first order fluxes?
Just first order.
But you have fourth order derivatives.
You mean so the chaos equation? Yeah. Sorry, I thought you were talking about the scheme accuracy. Yeah. I have fourth order. Yeah.
So the fluxes then, because if you integrate by parts twice, then you get to second order. So you have to impose the second order derivatives.
Right. So here, let's involve some like detailed sense. So how do I calculate the flux? I actually didn't use the subdomain average to calculate the flux. I actually just used those adjacent points that is very close to the subdomain interfaces. So if it's a fourth order derivative, I actually used 4 grid points to calculate the derivatives. So this is just for demonstration. So in real implementation, this
I'm not saying that. I'm saying not the points. It's a fourth order equation.
Yes.
So you need to impose second order derivatives.
So what do you mean impose second order derivative?
The fluxes, your fluxes.
Yeah, fluxes.
It's not just first order.
I derived yes, I converted everything to the flux, not just the original form. Yes. But I think in my implementation, it's a 3 order derivative.
Or another a related question: if you if you don't have a conservation equation, if you have a general equation that what would you impose for at the interfaces?
You mean still the missing the like incomplete non-physics?
No. Equations that are not in they're not conservation equations. They're not energy. They're not that type of.
Right. Yeah, that's a problem. Yes. So that's why I showed the 2D scalar burgers, not the 2D vector form burgers, because it just doesn't have that.
Yeah, maybe the papers of Ameya, C-pin and X-pin explain what I'm talking about.
Oh, okay.
In fact, there's a theoretical paper by Mishra on X-pin that shows what you need to impose.
I see.
But it's I know you want to solve just a
measure the fluid,
the fluids, but you actually use the Kuramoto-Zvazinski, which is not the same type of equation.
I see.
Yeah. If you use AKDV, for example, what would you do there?
I see. I remember I derived this form. Maybe it's just for 1D case. Yeah, for 1D case, I just calculate integration over each line. So there, for 1D, I think it's a special case. I can still derive that. Yeah, maybe for higher dimensional, then I cannot achieve this.
Okay. Anyway, Hen Hao, Fei Chen Hao.
Thank you so much.
Do we have any other questions for the speaker?
I see one question. Oh.
No. Yeah, it looks that we don't have any more questions. Thank you for your great talk. Thank you for your time, for joining us today. Thank you, everybody, for joining us today. It's time to close the session. Have a great weekend.